You. Good afternoon. Good afternoon, everyone. Welcome to our day number 4, although we are still covering material for day 2. But we'll see how to move along and reach to whatever target we've set. So we are going to pick up from where we left yesterday. So I want us to first start by, I'm going to show my folder. So it's really important that you know the working directory and you have all your materials, especially the files, into the working directory. It's in the working directory that all you can save your output, you can save your graphics using commands in there. And so the first thing is I have my folder, which is the exploratory and inferential. This is the folder that we saw yesterday. We open it, and then we saw these files. So we have Algeria width, which is a .csv file. That is mean it's comma-separated values. Then we have a PDF file. We have a R script, which ends with a .r file, capital R. We have another file, another file, .scsv, another .csv, another .csv, another .csv. Then we have a text file. Then we have another .csv. Now I know on the first day we saw how to get data from Excel, how to get data from CSV file. Now my advice is, please, there are different ways of doing the same thing. Try to learn 1 or 2 that you think you're comfortable with, and then you can use that. So if you find out that getting in data through Excel is disturbing you, you abandon that. You have your CSV file. My favorite is CSV file, and then I also have a text file. I also love a text file. A text file is very important. To me, a text file is one of, I like a text file because when I started using R, I was mainly using a text file. Okay, so you can have from your Excel, you can save it as a CSV file, you can save it as an Excel file, as the text file, but you can also directly get files that are saved in SPSS. You can get files that are saved in SAS. You can get files that are saved in Stata and any other packages. Any other statistical software. What you need to know is that you need a package that should be able to do for you the job. So I'm going to start by opening my script. And now script is very important. If you have everything in the script, you don't even need to save the output because you can always read the script. So I'm just going to click and say open with RStudio, which is a default. So now I can stop sharing my folder. I go ahead and share the Excel, okay. Let me now go ahead and share my R Studio. Okay, so here we have the first part of the script is always important that you install the files, the packages, and then you later call the packages. So once you install the packages, you don't need to install it again. So it's always good manners to try to, if you still want to keep them within your script, you put you make it become like just a comment by putting the ask symbol in front of it. So here, all the green line means R will read them as a script. So once already installed, the next thing is you need to call the library into function. So you can, if you don't call it, it will not come. So now that we have installed them, so we can start by calling them. So let's run line 3 up to line 19. So I go around line number 3. So when you are bringing in the libraries, red is okay unless it is unless it is an error or a warning, then you can install. So you need to run them. You need to run them. My colleagues will be there to take care of you in the chat and in the Q&A. Now, if you notice, when you look at the console, can you look down at the second window below the script? Now you can see mine, you can see, say error 4.2.2, and then it will also show you that it is desktop, forum training, exploratory. So that means once you open your script, the script can take you straight away to the working directory. So for me, I don't need to set the working directory. Now, if I also go down and look at where there are files, so if you go to the lower right window, you click files, it should be able to show you the file that are in the working directory. You can see the file that are in the working directory. So from there, you should know exactly what is going on. Okay, so I want to repeat the process of getting into the working directory for those who are, or those who want to be reminded. So what we are going to do is we are going to go and look for session. So when you click on session, you move and look at set working directory, and then you choose a directory. So you go to session, set working directory, and then choose a directory. You click choose a directory, then you go and look for where the folder that you want to make as your working directory is. You go and put the cursor onto the folder, not inside the folder. Then you click open, and then you should be able to be inside. And then at the end of the day, you'll have a line indicating that you have successfully run or successfully set up your directory. So I go to session, I go set working directory, choose a directory, and then I can go to my desktop. I look for my training. I look for that, I click OK. And then if you are successful, you should be able to, if you're successful, you should be able to have something like this. I'm going to copy this and put it in the chat. You should be able to have able to have something like this, but it should reflect on your folder, where your folder is, not my. So it should be able to. So this is what we have. Somebody saying cannot hear the sound at all, but I think you don't need to say, you only need to set one working directory. You're going to confuse RStudio. Why do you want to set two working directories? Okay. We are still using the material that has been put on day 2. So please, okay. So you should be able, so how many people have successfully gone into set a working directory? I want to see 111. Type 1. Okay. Type 0 if you have not. Okay, so we see that the majority of people have set their working directory. Okay, good. Those who have not set their working directory, please we're going to give chance to one person who has not set a working directory to be promoted so that we see what is on the computer. Can one person raise your hand so that you're promoted? Don't worry about whether you have the history or not, please. Okay, so anybody wants to try to tell us? Show us. We want to see why you're not succeeding in creating a working directory, in getting to a working directory. Okay, assume everything is okay. We proceed. Okay. So the next thing is we are into the working directory. You should be able to see the files that are in the working directory. So the next thing that we're going to do is we're going to start running lines. Okay. So yesterday we looked at the Irish line 24. You type and it will tell you about this data set called Irish. It tells you the format, it tells you the source of the information, and so on and so forth. And it's all written in simple, nice English that each one of you can read. And then line 25 gives us a summary. Remember, we talked about the 5-number summary yesterday. So we have the minimum, we have the maximum, we have the first quartile, we have the median, we have the mean, and then we have the third quartile. So from here, remember, Ellen told us that we need a $sign to be able to select a particular variable that you have in your data set. So if we want to know the variable that we have in our data set, we could simply use the word name. So I can type names, and then I put in bracket the data set, which is Irish. So once I have this, I should be able to run, and then it tells me that these are the variables that we have. The first variable is sepal length. The second one is sepal width. A third one is petal length. Then we have petal width, and then we have the species. Okay, so the species, so here, what we could do, we could also just observe the first few lines of our data set by typing this small command. Just type head, that is HEAD, and put the name of the data set in. Then you should be able to see the first 6 lines. So you can see the sepal length is 5.1, sepal width is 3.5, petal length is 1.4, and the petal width is 0.2, and then it tells you the species is called Setosa. Okay. You can also look at the last 6 observations by putting the word tail. So head and tail, and then you type the name of the data set, and you should be able to see the last 6 observations. They are coming from Vaginica as the species. So we have 3 different species, and we are going to look at the species are categorical in that it can classify whether you belong to Setosa or any of the other 2 species. And those are the ones that Ellen told us that we can convert them into factors, because then we can be able to use, for example, do analysis of variance and run that. So let's run our first plot, which is we want to plot sepal length versus sepal width. Remember, the first column is the sepal length, and then the second one is the sepal width. So we want to plot the first one versus the second one. No, we're using Irish data set. We just type the word Irish is a data set that is in R. Just run my command the way it is. Okay, do we see line? Can we go to my line 24? Look at my line 24. Line 24, you run line 24. Okay? So we are playing with the data which is inbuilt in R. So one of the data set is what we call an Irish data set. So if you run line number 24, it will give you information about this particular data set. Okay, so have we succeeded in running line number 24? Can I see 111 for 24? Please, if you are still installing R and R Studio up to today, I think that one we cannot help now. If there's any other reason why you're not getting that, then we can solve that issue. But if you are installing, please, I think you're late for today. Okay, good. So now let's go and you can read what the information that is provided down on the right, the lower window on the right. It tells you about this data set. It tells you this famous Fisher or Anderson Irish data set gives the measurement in centimeters of the variable sepal length, width, and petal length and width, respectively, for 50 flowers from each of 3 species of Irish. The species are Iris setosa, versicolor, and virginica. Okay? Then they go ahead and tell you how do you use the usage. It can be either Irish or Iris 3, and then it tells you the format. That Irish is a data set, a data frame with 150 cases. That is rows and 5 columns. That is what we saw here. If you look at when I ran the tail, the last observation had the last observation had 150, 150, 59, and so on. Are we together? Okay, so let's proceed. So the next thing, we ran line 25, which will give us a summary for the sepal length. So you can change what kind of summary you want to do here. And also look here, I've put a note here to indicate to you what each command is doing. So we can run the summary. And then I also introduce you to 2 simple commands. Head, that will give you the first 6 observations, and tail, that will give you the last 6 observations. Okay? Okay, so now let's run our line 26. So if you run line 26, you should be able to see a scattered plot. Now, this scatter plot, as on the x-axis, you have the variable on the x-axis is sepal length, and then the variable on the y-axis is sepal width. Now, if you click on top, if you see on top of the graph, there is what we call a zoom. If you click on the zoom, it will be able to expand that graph so that you can have a bigger view. Can we all click on the zoom? I don't know whether you're seeing you click on the zoom and you see. How many people have clicked on the zoom? Okay. So you should be able to see a bigger plot. But if you see from this plot here, this bigger plot that we have, you can actually see that we don't seem to have a pattern because it looks like the dots are everywhere. So in terms of what we looked at yesterday, in terms of correlation or drawing a line through the graph, we see that there seems to be no correlation between the sepal length and the sepal width. Now, but we still have, and we were told that these data as 3 different species. So we want to see, can we color our dots with 3 different colors to actually tell us what is going on within the data set, within the scatter plot. So let's proceed and run so somebody said that they had an error on line 25. Can you put the error on line 25 here and we see? If you got error on line 25, can you put it and we see? Put it in the chat or put it in the Q&A, then they will be able to help you run it. Okay, so now let's run our line number 27. So what we have in line number 27 now is we have added this particular small command. So we're saying COL color equals to Irish $ species. So we're saying go to the dataset Irish and pick the species, which is our variable, and use it to color the plot. So we can go and run line 27. So now if you zoom on line 27, if you zoom after line 27, let me try to stop sharing this, then I can share the zoom. So you can see from here that there is one species, the one in the black color. We will later label this. We can always put a key to this and you see out. So you can see that this one seems to have a positive correlation between the sepal length and the sepal width for this particular species. But for this other species, there is also some kind of a correlation, but the value is going to be much lower compared to what you have. But if you run it for the whole data set, you are less likely to see any relationship between the sepal width and the sepal or length. Is that clear to everyone? Okay, great. Okay, so now let's proceed and pick another set of variables. So the first one was we looked at the sepal length and the width. So now let's look at so now let's try to look at the sepal length and petal length. And we're still going to color with the species. So let's run line number 28. So if you run line number 28, let me stop and zoom, share the zoom one. Okay, so you can see now that the other black species that are colored black, there seems to be nothing going on here. But when you look at the other 2 species, there seems to be a much stronger relationship between the petal length and the sepal length. But you can also note that this particular species in black seems to have the petal length and the sepal length seems to be very, so these are the lips of this particular species are smaller compared to the other 2 species. Okay, so and this is their biological characteristics. Okay. So let's run, we change the species, we change again sepal length and petal width, we can run. So you can run this for the different variables that you have. And then, so let's run line number 30 and zoom for line number 30 so that we can see what is going on. So if you look at the petal length and the petal width, you can actually see these species here that they have smaller flowers. So you can see everything is crowded here, but the other one seems to have larger flowers and they seems to have their own relationship. But you can see from here that you can actually draw a straight line through the crowd and you will get, if you are to run a correlation, you will get actually a better correlation between the petal length and the petal width, irrespective of whether you're dealing with all of them at once or you're dealing with that. So you can see from here that the three species seems to be, they differ in terms of petal length. This one has smaller petal length followed by that, and then this one has higher petal length. So you can see from here that the one in green have bigger leaves, bigger flowers compared to the one in black. Later, we are going to see how you can actually bring in the levels. For example, you want to level the x-axis, the y-axis, you want to have that. That one you can build on with time. So let me continue. Okay, now what you notice here is that we have been presenting the name of the data and then the variable that we want to see. So like here, for example, we say Irish $sign sepal length. Then we come and say Irish $sign sepal width. Now, if we don't want to all the time put in the name of the variable, we just want to go straight away to the name of the variable and not the name of the data set, we can use a small function called attach. So what attach does is it picks the data set and keep it so that if you're going to bring in the name of any variable, it will look for in that particular data, in the data set that has been attached. So let's run line number 32. So this is our line number 32. Okay. Now we're going to repeat the same command that we ran. This is the same as command number 25, line 25. But instead of, we now don't have the Irish and the $sign. So we go straight to the sepal length. Okay. Have you all run line number 33 successfully? Can I see one? Can I see one for this one? Okay, I think we are moving on well. If you got an error, you can post the error and we see. My colleagues will be there to help. Okay, good. So we can repeat line 34, 35, 36 up to line number 38. They are going to give us the same drawing as we won before, but we've just, instead of putting the $sign, the name of the data set and the $sign. So in this case, what we're going to do, we are only going to put the name of the variable. The name of the variable, but the data set will be picked from what has been attached. So let's do the plots. We run 34, you run 35, you run 36, you run 38. Okay. Now, 39, what does 39 do? So 39 now will remove the data set from the memory. Okay, we are detaching it. So we attached it and then we can detach. So let's run line number 39. I always prefer that I run line number 39 a little bit more time so that I'm sure that will actually remove things from it. I can run it until I see the error. Okay, so are we together? Please put the question in the Q&A. If you have any question, you have any challenge, you can put it in Q&A. My colleagues are there full-time to able to help you. The chat is for saying yes and no only. Okay? Now I want us to go back again and draw a bit more graphics. So what I want us to do is let's run attach again. Run line number 43. And then you can say plot petal length and petal width and color with species. Okay. So let's run line number 44. Okay. So you can see from there. Now, the next thing that we want to do is we want to get a line of best fit into the scatter plot. And this is the beginning of what we are going to talk about tomorrow, the regression analysis. So we want to draw a straight line through our data point. And what this does is we use this command line number 45. So what does line number 45 indicate? That we need AB up line and what does? Now I can see people who are not romantic here. They don't know flowers. The flowers, the sepal length and sepal width, they're describing the different characteristics of a flower. You need to read more about, you need to read more biology and then you'll understand. Okay. So I want us to run line number 45 and see what will happen on our graph. Okay. So let me zoom the graph so that we can see together. Okay, so you can see we had our graph like before. We have petal length, petal width, and then we have the data points. And then we have also drawn a nice line through our data point. And this is the line of best fit. This is what we are going to talk about tomorrow. Susan is going to talk about regression analysis. So this is going to be the regression line, and this will tell us the slope, will tell us the point at which the line will cut the y-axis. So this one will be covered tomorrow. In the chat? Okay. Okay, let me see. There's an... okay. Now it's a bit... So let me check. Okay. Can you put for me the error in the chat? It's easier to get the error from the chat. The Q&A needs to you need to be responding. If you say petal length not found, that means you did not attach. First go and attach before you can run. No, detaching, with detaching, what you do with the detaching, you just need to click on that detach. Click it more than once. Click the detach more than once. Then if you see a red, we're telling you that there's an error, then that means you are successful in detaching. But it doesn't have to be, just click it once, and then we see why you need to click more than one is sometimes because you have detached more than once. You have attached more than once. How do you know which color belongs to which species? That is fine. We are going to look at how that is going to be handled later. Okay. So you can also now, with the line 46, you can now put the title to your graph. So you can add the title to your graph. So you can see now. See now we have a lovely title now on top of the graph. So you can actually change the title to your name and whatever it is, and you'll see it appearing there. The reason why I'm giving you I'm giving you these scripts is from now on, you don't need to actually be an expert in writing scripts for different analysis. What you need to know is that you need to know how can I modify a script so that I can use it to analyze my data. So what you need to know is, I need to know what are my variables, I need to know what's the name of my data set, and then from there I can actually go ahead and use the script that's already existing. There are a lot of scripts online. You just need to ask Google a little bit of question that I want to do this in R, and then it will give you several options. Then you can always follow. Why do we keep detaching? We detach because we want to free the memory. I'm doing detach and attaching now because I want you to practice so that you can get used to it. Okay? When you attach, okay. Okay, so now the other thing that we are going to see is you can set a lots of parameters. I mean, you can control the graph. Controlling the graph means you can decide the kind of space around your graph. You can decide on how big your graph should be. You can decide on what symbol to use to plot your data point. Like in this case, we use round circles, or we use circles, smaller circles, but you could also want to use a triangle, you may want to use a square, and so on and so forth. What I want us to do is, I want us to run line 50 and see what tells us. For now, you may not really pick that much, but this will tell us the current setting this will tell us the current setting of our plot. Okay, don't read too much into this for now. I want us to skip line 51 and run line number 53. So line number 53, what we are trying to do is we want to preserve the current setting so that if we modify our own setting, we can later come and give it back. Let's first run line number 53. Okay, then run line number 54. Okay, so we are going to go and draw a graph, and then we are going to see if there are going to be some changes within that. We run 56, 57. So now if you look at your data set, can you look at your graph and tell me what has changed? Just tell me what has changed. Okay, somebody said they have seen a triangle. The shape has changed. Okay, and they are also filled up triangles, the size. Okay. I'm going to try to slow down a little bit. Who is not seeing the triangle? We see colored triangle. The line of the line. Okay, now let's proceed and put line number 58. We'll put back our line. If you run line 58, we are going to get our line of best fit again. I'm going to explain what is in the graph here later, but for now, let's just run that. Okay, so let me. Okay, so you can see now the change that is happening here. Initially, we have a round points. We had circles which with empty inside, but now we've changed to triangle, and the triangles are filled up. And then the line that we drew through the data point now is no longer. It has a lot of dots now. It's no longer the thick line that we had before. So you can play around with this. You can change different things, but it will take a bit more time for you to actually learn and master this thing. So what my interest in this case is, first of all, you should be able to know how a simple R script look like. You should be able to interpret that script, and then you should be able to know what you can change in that script so that you are able to use it in your own data set. I'm going to slow down a little bit. I see now people saying I'm too fast. I'll try to. So any question that I need to address urgently as a general? Okay, say which command changes the triangle, circle triangle? It is line 54. See line 54. Line 54, the first thing is LTY. That means line type. And then PCH is the one that changes. So what we can do now is we can change this to say 18. Can we change line 54? Change 17 to 18 and then change 3 to 1. And then we can run the thing again. So if you change the numbers here, the whole thing changes. So you can see from here, let me expand a little bit. And then I share the screen. Okay, so you can see from here that we've changed into a diamond, and we've also changed the line. So you can decide what you want to, which of this you want, and the information is available as far as the shape is concerned. Let me see in the chat, are we together? In the chat, are we together? Yes. If the changes have not been observed, that means you need to rerun it again. please don't fear. What you need to do is you need to try to make some changes and then try to. So what you do is, let's go back to line 54. Let's change LTY to 2. Let's change the PCH to 20, for example. Okay? After you made the changes, you need to run that line again. Okay? So after, we can go ahead and run our line 56 up to 60, and then you see that the things have changed. So you can see now, we've changed now to smaller circles that are filled up. So you can always try different numbers to try to see whether what you want or what really happens. So you can also change the color instead of allowing R to choose for you the different colors. You can specify the colors that should be there, but that comes a little bit later with time when you've learned. So let's first try to learn the basics. After learning the basics, we can then modify and move on. How do I know which line type? There are lots of that is easy. That's the easier part. So you don't need to worry about that. I don't know which screen I'm showing now. It's still the, I'm using RStudio. Is RStudio which is being seen there? Okay, thank you. Okay, so if we go down further, if you want to know more about plots, you can click on, you put a question mark and you put the word plot. So this will give you that you want a default scatter plot, you want a generic, but for now, let's leave that. Let's try to run again line 64 up to, let's run line 64 up to line 71. So we start from line, what happened is now, we want, instead of having one graph at a time, we want to have 4 different graphs, but this is how we want them to be seen. We want two rows and 2 columns. So they're going to be 4 different graphs. So let's start by running line 64. I'll explain once you have the output. I know there are going to be challenges for a number of you. Okay, so let me first zoom. Before you complain, let me first zoom and show you what I have. Okay, so this is what we have now. So you can see that we're able to draw 4 different graphs together. So you can see the first one, we have sepal width with sepal length. And then the next one, we have petal length and sepal length. Then we have petal width and sepal length. And then we have petal width and petal length. So you can have your 4 different graphs, draw them side by side. And this is useful, especially when you want to demonstrate the differences, say, between different sites, different study areas. You can draw the same thing, but showing different relationship. Like yesterday, we were talking about looking at the scatter plot for current salary versus beginning salary for the different categories. So you can have for the different categories, you place them side by side, and it will be able to help you to solve the problem. Okay. So they are okay. Let me try and see okay. The other thing, what you see mainly, the margin is too large. Now the margin is too large, can be solved in different ways. Okay. I'm going to try to. Can I get one of you? Can we promote one of you to share, so that we can solve the issue of the who wants to share to show us? Aristides want to share? So there is Amolo Abbott, there's Deborah Chom. You can pick one of them. They have those ones who say me. Jolene, can you pick one of them? Promote one of them to.
We have promoted Erastus and Amolo Hebet.
Okay.
Yes. So Erastus, you can start. Nani? Amolo Hebet.
Also, there is Naomi Fosu.
Yes, I have shared the screen.
Yeah, we don't.
Can you be able to see it?
No.
You have not shared. Okay, now you're sharing.
Yes.
Yes.
That's what I'm getting. I'm not getting the 4 graphs.
Okay. Can you first? You see something that looks like a broom on top of the other console? At the edge, the right top corner of other console.
The what?
Other console. You know where you see your other console where there's the red?
Yes, I can see.
You click on that to clean up.
This one.
Yeah, click on that. Nothing's happening.
I already cleaned it.
Okay. Now what I want us to do, I want you to, okay, let's first go and okay, you start by running line 66. Okay.
I've done.
Yes. Can you run line 67? Okay. Run line 68. Okay. Run line 69 and 70. But what were you doing? Because it's working now.
I was running as you had instructed in the 60s.
But this is the instruction I was giving.
Okay, thank you. It has worked.
Okay, so you can detach. So another person, you can now quit.
Maybe they can indicate the ones who want to show so that we can promote.
Alemo?
Alemo, let me try to promote.
Try Alemo Melko. I see the thing here. So what you need to do is you need to try to adjust the windows where the graphs are and make it larger.
Boniface is promoted.
Okay.
Especially that door.
Boniface, are you ready?
Thank you.
Yes.
Yeah, let me just share my screen.
Okay, continue. George, what you to do, try to play around with the size of the windows where the graph is, make it larger. Okay. So what you do first, try to drag it on just put the cursor in between the two lines. The two lines that separate the windows into halves. No. Between your error console and where the graph appears. You see? Okay, try to see if you can make that line big. You can try to, oh. Where is he gone?
Okay. I'm here. Are you able to see my screen?
Yes. So I
Yes.
want you to you see the line between what is the, you have you see your error console?
Yes, this one.
And where the graph appears?
Yes.
I want you to try to pull that one to reduce the size of the script and the error console. Pull it a bit more. Pull more. Okay. And
Yes.
try to pull it also up a bit. No, up again. Try up now.
Okay.
Okay. So now let's try to start from running line 66 and we see.
Still not yet.
Okay, first go down. Go down to below detach. Okay, can you run line 72? Okay, go back and try to run line 66. Try to run the plot again and you see. Okay, can you go to view? You see the view up there? Click on that. Put exercise. Okay, try to run again. Try 66, line 66.
$67?
Yes.
Yeah.
Okay.
Okay. Yeah. It's now working.
Yeah, so you need to play around with that window and make it a bit bigger. That's the only reason is that. That's why you're not seeing it, but you should be able to see it. You're trying to zoom, but that's okay.
Okay.
Okay, good.
Okay,
so I think
you.
everybody should be able to solve that problem the same way. Okay, you can quit.
Okay, thank you.
Okay. Yeah, so everybody should be able to play around and then you'll have that. Now, if you're not displaying the 4 graphs, mean you're not running line number 66. So what line number 66 does, it creates that 4 blocks, and then you can run your 4 different plots. Can you all try and we see whether everybody is successful before we proceed to the next step? We are going to leave the graph now, and we're going to go and do other summaries. So how many people have succeeded when they adjust the screen? Okay. So great. So the whole thing is try to play around with the screen, the size, and then you also change the view to actual size. Once you do that, you should be able to see. There are other slightly more complicated and fancy way of doing it, but that one you learn it a little bit later with time. Okay. So I want you to run line 72. All of you run line 72 so that we can go and run line number 75. Okay, so line number 75, we are going now to call a data set. Now, if you saw in the folder, we had Algeria weight.csv. That is a data set that we have. If I click on here, this is the data set that we have here. You should also be able to open it somehow, but for now. So what we want to do is, we are saying, go to the folder, use this command to read this file here. And once you've read it, please put it in the memory as Algeria weight. That is the whole thing. So let's run line number 75. If you are successful, you should not see anything red in your R console. And then in the environment, you should be able to see Algeria weight, which shows that we have 1,344 observations of 5 variables. How many people have succeeded? Okay, now if you are not succeeding, means you are not in the folder. Okay, those who have not succeeded, please post, one person post the error and we see. No, that's not the error we're looking for. I want the error related to line 75. You are using read.excel. We are having read.csv. So Bernard, you probably not in the folder. Can you allow Bernard to share? Swaibu Bernard, can you promote Swaibu Bernard to show us what he's doing? Or Leon? Then Dungu Stanley, you have problem with the folder.
Shaibu has been promoted.
Yes, Swaibu, can you share your screen, please? Let me stop sharing. So can you click on the files above your drawing? Click on that file. Here, up there. Okay. Okay. So you first clean up the console. Click on that. Okay. Yeah, can you try to run line number 75 and we see? Can you go and open the folder where, can you, okay. Now what you need to do is first try to click on the Algeria with the one in the file, in the file. Click on that. Import as dataset. Okay, can you do import? Okay. What you probably do in the original file, it's a bit strange because it is showing something and then does not exist in the current working directory. It's a bit strange. Can you try to go to the file where you got it from, the folder where you got it from? Can you show me the folder where you got it from? You need to first stop sharing. Then when you go to open the folder, and then you share the folder instead of sharing if the folder is open on your screen, then you go to share screen and then show us the folder. Okay. The thing is, because now I have to drag up to down.
No, it's the current.
Mine shows upwards. Okay. So what I want us to do, okay, first open open one of them. I want to see the content. Open that. Okay. Can you copy the contents of this? Okay, you go and open, create another on desktop, create another folder on desktop. Okay, or put them in. Yes, paste it in there. Try to open it in Excel and I see whether it will work. Is it opening?
Yes.
It's opening.
Yeah.
Okay, now let's go and make this folder here your working directory and we try again. So you escape here and go to and then show us your okay, now you show us your other screen, that's the one before. The RStudio screen. Are you sharing?
Yes, I'm sharing.
Okay, we're waiting. Okay, so you go to session, set working directory, choose a directory. Desktop, day 4, and then open. Okay. Yeah, so let's try to run line 75 again. Okay, good. I think we are set to go. Okay. You can stop. So it probably the file that you took there, where the file with those dot, they were like mirror images of those files. They're not the actual thing. Okay. Okay, let me share my screen and then we can go to somebody wants to go to line. Okay. So line 70. No, line 72 is okay. What you see there is fine. The error that you see there is okay. That shouldn't be a problem. You're trying to put the thing back. So if you run line 72, you're going to see something that looks like this. There are warning messages. They're okay. Okay. Now let's run. Is everybody now satisfied with the line 75? Because you cannot do analysis unless you have the data. First. So who has problem with line 75? No, you first leave, those who are on the graph, first leave the graph now. It's not an Excel. It's not an Excel file. It's not an Excel file. Who is this one here? Okay. Okay, let's proceed. I know I'm trying to give instruction, but you guys are not following. Is there anybody with a challenge with line 75? Yes, Veronica, can you show us your screen? If it's telling you that no file means you are not in the working directory. Susan, are you in the working directory? Not this Susan, yeah, another Susan.
Veronica who?
There is Veronica, can you share?
I
No.
have 3 Veronicas.
3 Veronicas. Now the thing moves so fast. Try mail.
There is Veronica Maingi, Veronica Materi, Veronica Ogugo, Oliver. There is Veronica Ogugo, Veronica Materi, and Veronica Maingi.
Try Francis Mirara and we see. Otherwise, I'm going to assume that everything is okay. Okay, Veronica Ogugo says she's fine now, so that's okay.
Francis Mirara is come. Francis, the guy of the baby.
Hey.
Yes.
Guy of the baby. Okay, let me stop sharing mine, then he can share. Yes, Francis, you share for us the...
Not the baby this time.
So if he's telling you that you're not seeing the directory, so that means you have a problem.
Yes.
So can you first drag your thing, make it bigger? You're squeezing everything.
Yeah, maximize, yeah.
I tried, but mine is still giving me the error.
But first look at on top the URI. Where are you working from? Look at the R4.4.4, the R console.
Okay.
Where are you
I-
working from? Where's your directory?
From
You see you don't have anything there. First, let's go to session. Set working directory. Choose a directory. Please, you observe. Let's first see. Let's go to the file and you see what's happening. Can you open the file and we see what is inside there? Hey, but there's nothing in the file there. No, human, what are you trying to do? Okay. So now you can do the process and we see. You go show that your okay, try to run the line now. You should be able to work. You're already inside there.
Okay.
Okay.
Yes.
So you are so the issue here is that when you run the line reading the file, ARA will look for the data set. ARA will look for the data set in the folder in the working directory. So if it is not in the working directory,
okay.
Yes, can you stop, please? Okay, you stop sharing, Francis. Yeah, you stop sharing. No, go to stop sharing. Go to down. Go down where you started the sharing from, or you see where there's a red button. It says stop sharing. Okay. Okay, so I can assume for now that we all have the data set. The reason why I have to be a little bit fast is that we're not going to move anywhere. We still have a lot to cover. Okay, so line 75 or 74. And then I already told you what head does. So head will give us the first 6 observations. So you can see from here, you have site 1111, region BBB, rep, and then you have Adente, the B, and then you have the yield. So this is a data set that was got from a wheat experiment. So this is for a plant breeder. Those who do plant breeding, they know about multi-location environment. Now, so the head will give us the first 6 observations. The tail will give us the last 6 observations. Now let's learn line number 79. Okay, run line number 79. And please endeavor to read what is in the script, what is given to you. Say, this describes the structure of the data. So you can see from here, let's look at the console. The first thing here tells us that this is a data frame. Ellen talked about a data frame. We have 144 observations, 1,344 observations on 5 different variables. The first variable is called env, and here it is a character. CHR means this character, and characters are preserved for categorical variable. Now, when you go to the second one, it tells you region is also a character, and then it has B. Then you go to the next one is rep. Now, rep is an integer. You have I and T. The first value is a 1, 1, 1, 1, 1. Then there's gen, which is also a character. The first value is adente. The second one is bid, PD 17, and so on and so forth. And then the third one is numeric. These are numero, which has 3.5. That. So if you look at what we have up here, this is actually what it's trying to tell you. This is the first column, the second column, the third column, the fourth column, the fifth column, the fourth, and the fifth. So the first one is the environment, and it tells you this is a character. The second one is a region. It tells you it's also a character. And then the third one is a rep. It tells this an integer. And then the other one, it will have that. Is that clear to everybody? Okay. So we can, now what we want to do is, we want whatever is a character now, we want to convert it to a factor. That is what Ellen demonstrated on the first or second day. So that means we need to change environment into a character, into a factor, region into a factor, genotype into a factor. So we will leave rep and yield. Those are quantitative or, okay? So now let's move, and you can also use head, but this time you can have, you put a 3. That means you only want the first 3 observations. And then we can also look at the class. That is a data frame. You can look at n row, mean how many rows are there in this data set. So there's 1,344 rows. You can also look at how many columns are there, n col. There are 5 columns, or you can get the number of rows and number of columns at the same time by using dimension. So DIM means dimension. So if you run this line 91, it will tell you that the dimension is 1,344 by 5. That means there's 1,344 rows and 5 columns. The 5 columns are here. The first column has ENV. The second column has region. The third column has rep. The fourth column has gen. And then the last column has yield. Now, it's very important that you check this to be sure that you're handling the correct data set. Sometimes you have more than one form of a given data set. So the difference between an integer and integers are mainly discrete, while the numeric are mainly, they can carry decimal points, so they're more continuous in nature. Okay. So now what we're going to do here is then we want to change all the categorical variable into factors. You saw what Ellen did the other day. So what we are going to do here is that we are going to go to our data set, which is Algeria wheat. We are going to pick a variable called ENV. We convert that variable into a factor, and we put it back in with the same name. Okay? We do it for region, we do it for rep, we do it for genotype. So we can run that. Run 996 to 99. You should see no error. That means everything is running perfectly well. Okay? So now let's see the structure again. Remember, the structure at first was telling us there were characters, there was integer, and then there was numeric. So let's look at the structure again and see whether changes have been made. So here you can see from here that you see now tell us the environment now is factor now. It has 14 levels. So there's 14 different sites. Region is also now a factor. It has 2 levels. There's A and B. Then rep is also a factor with 1, 2, 3. Now we also change rep into a factor because this is also, you either belong to replicate 1 or replicate 2 or replicate 3. So that is also kind of a factor. And then the genotype is also now a factor, but yield remain numeric. You cannot calculate the mean of a factor because it doesn't make any sense at all. So you can see we're able to change from factor from characters to factor. So everything now is factor. Just briefly, Ellen already talked about this. I'm not going to spend much time. So what we can do, we can actually create new data set. So let's say, for example, we want to create a new variable called log yield. Instead of yield, we want to create a variable which is the log of yield. So what we do is we go to this is our data set. We bring the $sign and we put in the new name that we want to create, okay? And then on this side, this is what we need to do. So we go into our data set, which is Algeria wheat. You pick out the variable yield and get the log of it. So this is the statement, log of this, and then you put it back inside there. So let's run line 11111. Okay. Now when we run line 111, now what we are going to do is let's run our line 113. With line 113, we're able to see, we're able to view the data that we have. Okay. So you can see from here now that initially we had the ENV, we had region, we had rep, we had gen, we had yield. Now we also have a new variable which is called the log yield. That's the variable that we created. So you can see the log to base 10 of this will give us that. The log to base 10 of this will give us that, and so on and so forth. This is part of what we call data transformation. So you can also do data transformation in that way. Okay. We can do a summary for yield. The variable of interest here is yield. So we need, this is the data set. We get the $sign, and then we get the name of the variable that you have there. So let's run line 116. So it'll give us the summary like what we did before. Okay. We can also convert a quantitative variable into a binary or into two classes. Okay. So here, what we are going to do is we are going to look at, we're going to create a new variable, which we call yield category. Okay, so this is going to be a new variable. Now in this new variable, what we are going to do, we are going to use this simple, there's a simple function here. If else, if it is this, it should be this condition, else it should be the other one. So what we are saying in this case is that you go to the Algeria wheat, picked the variable yield, okay? Now, if the yield value is less than 1 point, 1.852, you make it to make it low, else make it high. So in this case, we're going to create a new variable that will only have high and low, high and low, high and low, high and low. Because of this, say if, else. So this is the function. This is the test. We're saying that if the yield value is less than 1.85, make it low, else high. So let's run this, and then we view. Okay, so you can see here. So 3.502 is higher than 1.8, so it's taken as high. So you can see here you have high, 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 high. Then you go down, you get low, you get high, you get low, you get high. Not high on drug or on alcohol. It looks like everybody's interested in adding on WhatsApp or not. Hey. Okay, that one we can talk after. You can, after getting us after the training, we can talk about it later. Okay, so you can also name, you can also change the name. Now, what I've done here is that we have a nice small comment here that tells you what each of these things does. So here, for example, we're saying, okay, you go to the Algeria wheat, and what do we want you to do? We want you to rename, okay? We take, and what we put as the environment, we want it to become site. So site is going to be a new variable, a new name that is going to move out. So let's run line 1, 2, 3. And then we can look at the names, what we have, whether we have changed the thing. So you can see from here, initially we had remember initially we had ENV, now it is called site. The rest remains the way they are, okay? But you can also change everything in a line like this. So I said, change, the first one should be site, the second one region, block, and so on and so forth. So we can run this and then check that, okay, the changes have actually been made, okay? Then I'm not going to run this. What are you doing in line 50? Now, this one, now you can help and we see. Okay, are we together? Okay, so who has got error? You can't find function rename. So if you don't find the function rename, that means you don't have, it's supposed to be part of a function deployer. So that means you have not, either installed or called the deployer function or package in. So that means what you need to do is you need to go up. Let's go up to where the packages are. So this is where your scene will catch up with you. Did you run line 19? Look at my line 19. First run line 19 and we see. If you run line 19, then you should be able to go back and run the others without any problem. If line 19 brings you problem, then you need to run line 18 first. If you want 3 categories, that is fine. You need to pay me more money, then I'll teach you how to do 3 categories. Let's first get the simple things first. I will get to the other one later on. So you should be able to sort out the rename issue when you bring in the deployer. If you don't have the deployer, you won't get it in. Okay. I'm going to skip, but you can run 132. It just gives you 132, 33. So this is just how to specify the rows and columns. We're not going to spend much time in. Ellen talked about subsetting. So we could actually subset and get only region B. Remember, there are 2 regions here. There's region A and region B. So we could actually create a data set called Algeria region B, and then we can use this command here to run. So let's run 135, and then we can view. So you can see everything. Yes, B, B. So you don't have A because you've subset. You only created B as part of that. Okay. So what are we trying? In line 139, this particular line here, we are only selecting one variable, and that one variable is yield. So the $sign is always used to extract a variable. So if we extract a variable here, you see it shows you all the variable that you have. So we can also just get the mean of that variable that you have there. And the mean is 1.85, and that was the value that I used up here in creating, when I tried to create this line here. So I say if the value is below the mean, make it become a low yielder. If it is above the mean, then make it become a high yielder. That's when you create the high and the low, as we saw before. Then we can also do tables. The tables are there. So what we want to do here is we are trying to look at, we are trying to do a cross-tabulation. We want to see site and genotype. So we want to see we want to count. This is just a table just for counting purposes. So let's first run line 152, then I'll explain the output. So let's run 152. Now, R that's what we call object oriented programming. So R creates objects, and once you create an object, you can do anything to that object that you created. So in this case, we have created an object called my table. Now this object called my table, we can then decide to say, well, I want to get only, okay, let's first try to see if we can print this table here. Okay, so you see now this is the table that we've actually got here. So this table tells us that at site 1, there are 4 plots with Adente. There are 4 plots with B Dura 194. There are 4 plots of this. There are 4 plots of that. There are 4 plots of that. they are proposed of that. In this case, you want to check whether you actually have the same number of count in all the different cells in your table. So this is what literally this table does. So the table that it does a cross tabulation, and cross tabulation in this case is simply you're trying to count and say how many are in this category, how many are in the other category. So that's what we have here. Then you can also decide to just look at the percentages on the, like what we say we have remember when we are doing the margin of the table, we're doing the margin of the table. I'm not going to spend time on this too because it's not that valuable for now. What I want us to do now is I want us to start doing some tests. So what we have done so far up to this point is we got our data set in R. We tried to look at the names of the columns. We tried to look at the dimension of our data set. We did some simple summaries like the mean, we didn't calculate it, but we look at the 5-number summary plus the mean. Now, what we want to do now is we want to try to do some hypothesis testing. So the first thing that we are going to do is now we are going to do what we call a t-test. A t-test is used for testing if there are differences between two populations, but it can also be used with one population. So as far as the t-test is concerned, we have 3 types of t-tests. We have what we call one sample t-test. We have 2 sample independent t-tests, and then we have 2 sample dependent t-tests. So we're going to look at the different types of t-tests, and then from there we are going to progress, and we're going to look at the alternative to t-tests if you're dealing with non-parametric tests. So we're going to look at some non-parametric tests. So at this point, let me find out whether we are okay. The speed is too much. For the table now, let's forget about the table for now. At least from what we have, how did you make the table visible? Oh, how did I make the table visible? I just highlighted the word my table and I ran it, only the word itself, the word my table. That's how I broke it down. So, okay, let's have a 6 minutes break. Let's have 6 minutes break. We are going to start at yeah, tomorrow is yours. No, I can't. But I'll try to finish the.
Thomas, if you might be presenting, but you're muted. Thomas, you're muted. So in case you're talking, the audience is not getting you.
Okay. Oh, back. So I want us to try to go through the remaining 1 hour, see how much we can cover. So the t-tests, analysis of variance, regression analysis belong to what we call the parametric statistics or parametric data tests, while things like Whitney-Mann's U-test, the Wilcoxon sign ramp test, Cross-Wallis, Friedman test, those are tests that are considered to be non-parametric in that you don't put emphasis on the parameters. They like the distribution of the distribution, like we want a normal distribution. In this case, we have a distribution free kind of thing. So they are mainly based on ranks. You analyze ranks instead of analyzing actual value. They produce slightly different type of statistics, but they all come to the same conclusion. Okay, so we are going to use a small data set, which we call pollination.csv. Now, this is a data set in which a plan, somebody had an experiment in which some flowers on a plant, some flowers are self-pollinated, while on the same plant, some flowers are cross-pollinated. So let's first call the file. So we run line 162. And I want us to have a look at the line. So let's type view my data. Okay. So what you see here is then that you have mother plant 1. So this is the plant. Then there are some flowers that were cross-pollinated and some flowers were self-pollinated. So on plant number 1, for example, the cross-pollinated flowers on average had about 9 seeds, while the self-pollinated plants on average had about 6 seeds. And then this one had 21 versus 17. This one had 24 versus 23. So you can see from here that we seem to see that the plants that are cross-pollinated seems to produce more seeds compared to the plant that are self-pollinated. Okay, so this is what we call paired sample, paired or dependent sample, because you can see these two values are coming from the same mother plant. That's why it is paired. They are paired. They come from the same mother plant. This is different from independent. Independent means the two observations are not related in any way. So this is what we call a paired sample, and we do what we call a paired t-test. So we can also go ahead and look at the first 6 observations. So you can see plant 1, plant 2, plant 3, 4, 5, and 6. And then they give you the different number of seeds in the self and then in the cross-pollinated flowers. We already saw how to use attach. If you don't want to be pulling all the time, putting in the $sign and then the name of the variable, we can just do attach. So let's run line 164. Okay, after running line 164, we come and this is the line that does the test. So you can see from here that the function that does the test is called t.test. If you look at, so we got here, we have the cross-pollinated. This is the line here, compared with the self-pollinated. And then here you want to tell whether it is a paired sample or not. And for us, we say this is a paired sample because the first two observations belong to the same mother plant. The second two observations belong to the second mother plant, and so on and so forth. So in this case, these readings are paired, okay? And then the alternative is two-sided. So two-sided here is, we are looking at, we're saying in this case, for example, we say that the mean of cross-pollinated flowers is different from the mean from self-pollinated flowers. We are not interested in which one is bigger than the other one. What we are interested in that at least they are different, and being different, that means it's two-sided. If the self-pollinated is bigger than, has more seed than cross-pollinated, that will still qualify as different, or if whichever you look at it. So this is what we call a t-test, and then this is paired t-test. There are two samples that are paired. So let's run 165. Okay, we all succeeded in running that. I repeat, line 165. Okay, so in line 165, we have, this is the first one column. We are comparing cross-pollinated with self-pollinated. So these are the two columns that we are comparing. Now, this is asking us whether we are doing a paired t-test or an independent or non-paired t-test. So in this case, we are saying paired equal true. We are going to see the same thing if you run and say paired equal false. That means you're saying the two columns are not related, but we know that the two columns are related since the two observations come from the same mother plant. Then here we have the alternative hypothesis. So the null hypothesis always say there is no difference between cross-pollinated and self-pollinated flowers. Now the alternative can be stated in three different ways. The first way is, we can say there's a difference between the self-pollinated and cross-pollinated. That is the first way we can state the alternative hypothesis. The second way we can state the alternative hypothesis is that cross-pollinated have produced more seed compared to self-pollinated. And then the third alternative could be self-pollinated produces more seed compared to cross-pollinated. So here we're looking at the two-sided. So we run the two-sided, then we come and look at the results. So when the result pop up, the first thing is we are looking at paired t-test. So when it is paired t-test, that is, we already know why it is paired t-test. Then the data is, we are saying we are comparing cross-pollinated and self-pollinated. Part of the result, then we get the T statistics. This is our T statistics. So can I see in the chart what is the T statistic that you've got? If cross-poll is not found, that means you did not do the attach. If you've not got the result, if you say cross-poll is not found, that means you did not do the attach. Okay, good. Okay, so T is 15.4, and then the degrees of freedom is 19. Then the p-value is 3.404 times 10 to the -12. Now, what we want to do is we want to compare the t-value here with the p-value here with alpha. So alpha is the what we call level of significance. So by convention, the level of significance, the most frequently used, we have 0.05, which is 95% confident. We have 0.01, which is 99% confident. Then we have 0.001, which is 99.9% confident interval. So the comparison here is that we are going to compare the p-value with the significant level with alpha. So if we compare 3.4 times 10 to the power negative 12, so that is more or less equivalent to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be the value more or less. So this is 0.000034. Now we want to compare this value with 0.05 or 0.01 or 0.001, depending on the level of significance that you have for yourself. So you can see in this case that our p-value is very, very, very small compared to any of the significance level. So, and we always conclude that the p-value, if the p-value is smaller than the significance level, then we reject the null hypothesis. So when we reject the null hypothesis in this case, we conclude that there's a significant difference between the cross-pollinated and the self-pollinated flowers. And in this case, the difference of 3.4 means on average, the self-pollinated, the cross-pollinated flowers produce 3.4 seeds more than the self-pollinated. And this is based on the order in which you put this. So if you change the order, then you're also going to change. So if, for example, we put self-pollinated here, the sign is going to become negative, but it's still going to be so you can see from here that the t now become negative, and then the difference also is negative 3.45. So in that case, the difference is the mean of this minus the mean of that. Now, in this case, if the alternative is two-sided, it doesn't really matter. You will always get the same result, irrespective of which one comes first. But if the alternative is either greater than or less than, then you're going to get different results. Are we together? If there's any question that you feel, you can ask in the Q&A. My colleagues will be able to help you out. If cross-poll not found, that means you did not attach. So go and attach, run line 164 first before you first start by running run line 162. Then you run 164, then you can run the other one. Okay, so the conclusion is here. Okay, so what we do is we compare p-value. Let me first clean so that I can write on the. So what we do is we compare our p-value versus the significance level. So the significance level can be 0.05, can be 0.01, or 0.001. So here we mean you are 95% confident. In this case, you're 99% confident. And here you're 99.9% confident. Okay. So that is what we have. What we do is we compare the p-value with the level that you've set. So here in this case, for example, if we set ours at 0.05, that means we need to look at our p-value, which is very, very small compared to any of these. So since the p-value is less than the significant level, we can conclude that there is a significant difference between cross-pollinated and self-pollinated, with cross-pollinated performing better than self-pollinated. Okay, because if we look at the difference self minus cross, you get a negative 3.4. And this difference can be when you change the order in which you have them. Okay? Now, we can also, just for trial purpose, we can decide to ignore the fact that this thing are paired. Let's say paired equals false, and we run, and then we see exactly what's going to happen. Now, when you say pairs equals to false, now what happens then is that it also wants to ask you another one. What about the variance? Are the variance in the true group equal or not? So let's run this, and we compare the results. Okay, so you can see from here that things have changed. Everything has changed. The t-value has changed. In our case, the t-value was 15. In the first case, the t-value was 15 point something. Now the t-value is just 1.99. The degrees of freedom has increased because now we don't treat we don't treat a pair as related, so we count each pair as independent. So that means from 19 degrees of freedom, our degrees of freedom is multiplied by 2. We got now 38 degrees of freedom. So in this case, the higher the degrees of freedom, the higher the pieces of information that you're likely to pick, that you're picking from the data. But what we see in this case is that because this is coming from a paired observation, if you treat it as unpaired, then you tend to overestimate the degrees of freedom. This one actually, degrees of freedoms have doubled. Because each observation, although they come from the same plan, we now treat them completely like they're different from each other. So you can see that we are almost, the result is almost marginally significant. Okay, because we've changed and we changed the assumption that from being paired to unpaired. Okay, so let's run detach and then we come back later. Are we together, ladies and gentlemen? Can we? Yes, you can test at 90%, but you see, if you test at 90% means you're willing to accept error of 5%. You can even test at 50%. That means you're 50-50 whether the error. So you can see, that's why we want to go and make it as little as possible. You want 5% because you want to be more confident. So you can do the degrees of freedom is related to the amount of information that you get from the data set. And in most cases, the degrees of freedom is given by the total number of observation minus 1 for the case of a t-test. And now here we have two scenarios. When we consider our data set to be paired, that means the two pairs no longer contribute independent information. Their information are related. So from the two pairs will constitute one set. And that is why here we have 20 different plans. We have 20 different plans, and each plan contribute one piece of information if you consider that to be paired. And that's why you have 19 degrees of freedom. Now, in the case of consider this to be unpaired, what will happen is then that you disentangle the two information that come from the same mother plant. You consider them as two different pieces of information. That is why our degrees of freedom now move from 19 to 38, because you're multiplying 19 by 2. Okay. You don't set the p-value. The p-value is what gets out of the data. What you set is you set the significance level. Now you can set whatever significance level you want as long as you can defend it. Yeah. So if you want, if you can say you want significance level of 0.8. 0.8, that means you are willing to accept error of up to 0.8. So you're only 20% confident. So it is up to you to decide whether you want a higher error or a lower error. That will depend on you. But it will determine, it will influence people's ability to believe in your studies or not. So whether you're in social science or whatever it is, at the end of the day, you need to be able to convince people that you are doing something credible. So if you're saying, well, it's 50-50. So you can say if you're a medical, you're testing medicine and you tell people, well, it's 50-50. You can get cure or you may not get cure. Who would want to try 50-50%? Okay. Okay. Now I want to proceed a bit. So now I want to change a little bit. How do we know which confidence level to use? It all depends on, okay, statistically, we are stuck with the 0.5 or 5% error or 1% error or 0.1% error based on the work that Fisher did sometimes back. And nobody has come up and said maybe 10% or what. But the argument has always been that do we really need to depend entirely on the p-value? Do we want to really look at everything in terms of the significance level? Because you can have a p-value that is very small, but then the effect that you're trying to test may actually not be very, very significant in real life. Now, if, for example, let's say you're comparing two different varieties. Now, if you're comparing two different varieties, and let's say, for example, there is a variety that is already on the market, and then you want to introduce a new variety. Let's look at maize. Maybe most of us know maize. Let's say you have a new variety called X that is already on market, and it produces 600 kilogram per hectare. Now you come and come up with a new variety, variety T, that produces for you 605 kilogram per hectare. Now that the difference of 5 kilogram per hectare may be significant, but in terms of the practicability, would you want to introduce a variety that performs slightly better by 5%, by 5 kilogram? I mean, remember, you need to produce the seeds, you need to put in extension, you need to do all those things. So at the end of the day, it will not actually make sense. So there is statistical significance, but there's also, in terms of the practical significance, may also determine whether. So the p-value can be used as a guide, but it's not necessarily the main thing that will decide on what needs to be done. Okay. So let's proceed and do Wilcox test. So the Wilcox test is a non-parametric, is that it doesn't make assumptions about the distribution of the data. When you're running a t-test, the assumption is that the variable that you're dealing with should be normally distributed. Now, in this case, we don't need to know anything about the distribution of the data, but we can also test one variable at a time. Let's say, for example, for cross-pollinated flowers, we want to test whether the mean of cross-pollinated flowers is equal to 15. So in this case, what we're doing is that we are not dealing with paired kind of situation. We're saying paired equals 4. So here we look at the cross-pollinated seeds. Let me first try to try to do this. I did. I just want to try to illustrate something here. Okay, so when you look at our column number 2, you look at column number 2 here. You find here that the first plan, the cross-pollinated seeds, there are about 9 seeds. The second one is about 21 seeds, 24, 16, 17, 19, 22, and so on and so forth. Now, if I want to test whether these values are actually equal to 15, let's say there's some theoretical basis. Somebody comes up and said, if a flower is cross-pollinated, on average, it should give for you 15 seeds. Now we want to test the data that we have. Does it really confirm? Does it come from the same population with 15 seeds? So we can do what we call a one sample test. One sample against some fixed value. In this case, our value is 15. So we can test whether the cross-pollinated have a value that is equal to 15 or not. Oh, I detached already, so I need to still attach before I can run that. Okay. Yeah, I think, okay, fine. Let me first run this, then I'll come back and try to explain it again. So what we want to do here is that we want to, okay, let me try to explain what one sample test could be. So let's say, for example, in the town in which you live, you have a bakery that claims that they make bread that is 1 kilogram. That is the claim. So we say on average, our bread is 1 kilogram. Now, if you go into a supermarket and you sample, say, 15 loaves of bread, you want to confirm whether the claim that these people, the 15 kilogram that they set, is actually true or not. So remember here, you're picking all the bread sample from one supermarket or from one bakery, and you want to test, is the mean really 15 or not? That is what we call a one sample t-test or a one sample non-parametric test. So in this case, we are not dealing with a paired sample, we're dealing with one particular sample, and then we're saying, is this value different from 15 or not? So we can test this. Okay, so here you do what we call the Wilcoxon signed rank test, exact test. It tells you you have the data in this case is the cross poll. You picked only that particular column for cross pollination, and then you calculate the statistics. And this statistics is in this case you have a value of 194. Then you have a p-value of 0.0003223. Here you're testing the alternative hypothesis that the true location is not equal to 0. Remember, the null hypothesis is that the null hypothesis in this case was saying that the bakeries are telling the truth. Their bread on average weighs 1 kilogram, or let's say 15 grams, what you would say so. So now you're testing that, and then you're either going to reject the null hypothesis or you fail to reject the null hypothesis. So here we still get our p-value, and we compare this p-value with alpha, or the significant level, as we indicated before. So you can see from here that our p-value is less than 0.05. So in that case, we reject the null hypothesis and conclude that the true weight, the mean of this sample of ours is actually not equal to 15. Okay? It's not equal to 15. Now let's test for the second one, for the self-pollinated group. When you test for the self-pollinated group, you can see we have the statistics is about 148 and the p-value now is 0.114. So can anybody interpret for us this p-value 1. Can anybody interpret for us the value? What does this mean? The 0.114. Not significant. That's somebody say not significant. Okay, so we are comparing 0.114 with 0.05. Remember, we say we reject the null hypothesis if the p-value is less than alpha. In our case, the p-value is not less than alpha, and therefore we don't reject the null hypothesis. If we don't reject the null hypothesis, that means we are saying there is no significant difference between the value, the sample mean, and the fixed value that we have. So we fail to reject H naught. Okay. I'm going to okay, let's run line 174 first, then I'm going to do some kind of repeating. So now when you look at line 174, 174 is very similar to what we did before. Look at our line 165. Okay. So everything in line 165 are almost the same without, except the test is different. Okay. But it's this paired. We have the cross versus self. So this is actually the non-parametric alternative to this. So they are supposed to produce for us similar results. Now, when do we use non-parametric? We use non-parametric when assumptions are violated. When the assumptions of a t-test are violated, then you can go and run your non-parametric, which does not require any assumption. It uses rank. Non-parametric statistics are mainly used when you're dealing with very, sometimes very small samples. Okay, so let's run 174 and then try to see the results. Okay, so it tells us here that Wilcoxon rank exact test. The data is cross-poll and self-pollinated. So you're comparing cross-pollinated with self-pollinated. And then you have a statistics of 210. And then you have a p-value of 1.907 times 10 to the power -6. Now let me run this first one as well so that we can compare. I'm going to run the t-test also and we compare the results and see whether we get the same results. Okay, so at the end of the day, the p-value are what we are going to depend on. So this is 1.9 times 10 to the power -6. And then this is 3.4 times 10 to the power -12. So you can see from here the p-value for the t-test is much smaller because a parametric test is a lot more powerful compared to a non-parametric test. We mainly use non-parametric when we have no alternative, when we feel like things are not working out completely. So that is what we have here. So you can see that the two tests, they're all testing the same thing, comparing the two groups. Okay, they're all paired. The only difference is that here we don't need to make assumptions about normal distribution or any other. So in both cases, we still found the same result, but the difference here is in the p-value. This one has a much smaller p-value compared to the other one. And that means that the one with the smaller p-value is a lot more powerful compared to the one with a bigger p-value. I don't know whether I'm making sense or not. Why parametric? No, I did not show you where the data are significant. I'm just trying to make we don't have that much time for now. What we're trying to do is we are trying to first compare to show you the alternative, but you're all postgraduate students, so I expect, and researchers, so I expect that you can, after this, you can go sit down on a computer and try to understand more. No, I'm not confirming that the t-test is more powerful than based on the small p-value, but what we know statistically is that the parametric tests are more powerful compared to non-parametric tests. And one way is looking at the p-value. The p-value is related to the power of the test. Okay. I say, when can we use a t-test and when can, this is what I've been talking about. I've been trying to explain. A t-test is used, the assumption of t-test is mainly that when you have a normal distribution, but for a non-parametric, you don't need any assumption in relation to the distribution of the data set or the distribution of the variable that you're handling. Okay. I still have one more t-test to do, but this is now the one that is independent sample. So we have a data set here of this small animal called newts. So what somebody did here was to measure the length of the animal. And then we want to compare the length of the male versus the length of the female. So in this case, we are dealing with two samples. We have samples of male and samples of female, and these samples are not related in any way. And this is why we use independent sample. We call them independent sample. In the first case, the samples were related because the part of the flowers were from the same plants, were self-fertilized, and a part of it were cross-fertilized, and then we made comparisons. So from the same mother plant, we have two data points, and those data points are related, and therefore, that's what we have a dependent sample compared to independent samples. Okay. So what happens is that what we do is we test the null hypothesis. Once you do a testing, the testing is based on the null hypothesis. So there are two options. You can either reject the null hypothesis. If you reject the null hypothesis, that means you're saying the alternative hypothesis seems to be true, or you fail to reject the null hypothesis. Now, when you fail to reject the null hypothesis, then we conclude that there's no difference, significant differences between whatever you're comparing, because the null hypothesis says there is no difference. Then the alternative is the one, if you reject the null hypothesis, that means you're going for the alternative. So that you are saying, based on the data that you have, there's evidence that there's statistical significance between the pairs that you're trying to, whatever you're trying to compare. So in this case, for example, if we rejected the null hypothesis, so we are saying there is a significant difference between the cross-pollinated and the self-pollinated flowers. Now, because we are talking about that, just the difference between them, we are not interested in which one is higher than the other. Now, if I state my alternative, if my alternative hypothesis states that cross-pollinated flowers perform better than the self-pollinated flower, that is what we call a one-tail, and that one tail will be considered greater. So what we could do, let's move up here a bit. So let's say instead of saying alternative two-sided, let's say alternative greater. Okay, I'm going to change this and say greater. Oh. Oh, I'm not supposed to have a. Of. No. The main assumption of a t-test is that the data has to be normally distributed, and secondly, that if you're doing independent samples, that means the two samples are supposed to have constant variance. Those are the two main assumptions of a t-test. Now, I'll ask you to go and read that on your own. Okay, so you can see from here that we can have alternative as greater, but you can also have alternative as less. Now, if I put it as less, that means I'm saying that cross-pollinated is less than self-pollinated, which is not true. So the result should actually show us that. So when you do this, you can see the p-value is 1. That means the self-pollinated is not greater than the cross-pollinated. So there are 3 different hypotheses here. You can say two-sided, in which case you're not interested in which one is greater than the other. You're just interested that the two are different. Or one-sided, where you can say cross-pollinated is greater than self-pollinated. Or one-sided, where you say cross-pollinated is less than self-pollinated. And if you change, you're likely to change the results. Okay, so let's proceed a little bit. Otherwise, we are not going to go anywhere. Okay, so let's get this data called the newt. Let's run line 177. Okay, let's run line 178 to 79, and then we run line 180. Okay, I want to show. So what we did here is we are trying to draw a box plot for the length, but we want to have separate for the male and the female. And we want the Y level, this is Y lab, meaning the Y axis to be level, the length in centimeters, and then color should be green. So let me first stop sharing this, and then I can share the. Talked about this several times. Okay. So what we want to do for now, I just want us to show. I want to show you the. Okay, let me stop the sharing first. Okay, so from, okay, just hold on a bit. Let me share my screen back. Okay, so from here, you can actually see the female. The female have higher, longer, about up to about 19 centimeters. The males are shorter, about 14 centimeters. But you can also see from here, which seems to see we seem to see that there seems to be a lot more variability among the male compared to among the female. And remember, one of the assumptions of a t-test is that there should not be significant difference in variation between the two populations. So what you can see in this case that assumption may actually be violated. Okay. So from here, we can go ahead and do the test. Now, if we look at line 181, let me try to explain what we have there. So the first thing is we have a t.test, which is the same as what we had before. But here, paired equals false. In the previous case, we said paired equal to true because we said it's paired observation. Now, then there's another one here, var.equal. Are you going to assume that the variability in the male and the female are equal? We can say true if we want to assume that the variance are equal, or we can say false if you want to assume that the variance are not equal. Now, they will produce slightly different results. We are going to run with true, and then we are going to run also with false. Okay. So, and then this is what actually happened here. So here you have the length. Okay. The length, you want to compare the length of the two sexes. So here you have the length as the variable that you're interested in, and then you have this small tilde sign, and then you have sex. So let's run this, and then we see what kind of results we are likely to get. Okay? So the first thing that we see on top here, we have two sample t-tests. Okay? Then data, look at the data. The data say length by sex. Then we have the t-value like we have before. We have the degrees of freedom like what we had before. And then we have the p-value that we have. So based on the p-value, is there significant difference in the height of male and female? I want to see in the chart. Okay, I can see yes. Only 2 people have answered. If you do analysis and you see error in error, that means you are doing something, you are working. If you don't see error, then so if you see error, it's okay. And once you see error, that is okay. Okay, we are going to ask somebody who with an error to show us what they have. Okay, so let's look at the interpretation. A number of you have got. Okay, so can we ask there's the Chuku. Chuku, can you share for us your screen and we see what is happening? Yeah, if sex is not found, that means you probably not attached. I want somebody who wants to share the screen so that we can see where the error is coming from. Michelle, can you promote Michelle?
I've promoted Ichuku.
Okay. Yeah, Shuku. Can you show us your screen?
Chuku, go ahead. Chuku. So Mark, maybe you first stop sharing yours.
Oh, sorry. Okay.
Chuku, go ahead and share yours.
Okay, so you start from line, okay. Can you start from line 298? Okay. Run attach. Okay. Yeah, okay. Okay, you run that and we see.
So that's what is showing.
Okay, just remove the pair dot. First remove it. No, I mean you edit your command.
Okay, which of the command?
No, that line 302. Can you remove pair dot? No, go inside. Remove pair dot the paired.
Completely.
Okay, first remove that. Remove one of the commas. Run and we see.
Yeah. It's right. Okay.
I know.
And I have it.
Yeah, sometimes it behaves in a funny way, but that's okay.
Okay.
Yeah, I for some reason I don't know why it's refusing to run it that way.
Can I stop here?
Of course, the thing here is then that when you look at it in this way, it's a bit difficult to. You can stop sharing. Any other person that some the. Okay. You try to see the once you see the solutions. Okay, solve. Okay, if it is rectified, that's fine. Okay, great. You can stop sharing now. Shuko, you can stop sharing now. You're going to intimidate my people.
Sorry?
You're looking. I say you can stop sharing. You're looking very serious. You're going to intimidate my students. Okay, okay, let me share and I'll go back to my. The reason is, okay, in this case, well, I don't, error sometimes behaves in a funny way. I just don't, maybe because my version is an older one. I think I have 4.2.3. It could be something like that. But for now, what we see clearly from here is that sometimes you need to go beyond, try to explore certain things. Okay. Now we can run the alternative. That is the Wilcox test. This is now for independent. This is the same as okay, let's run that. So it kind of also gives you the same results, similar results. They're all significant, but then you get a lot more information from the parametric compared to the non-parametric values. Okay, let's see. Oh, we are already time bad. Can we get 10 at extra 10 minutes to run this? Then okay, so you have already installed cars and you probably call. So what we can do remember when you look at the graphs here, we have there seems to be a lot more variability among the male compared to the female. So what we can do is we can use Levin tests to actually test where the variants are significantly different among the two groups. And if the variants are significantly different, then we need to modify our test so that we can, instead of say var.equal true, we can change it to false, and then you can actually see that we have different results. So what we can do now is let's run a Levin test. Okay, and then we run line 8. Okay, so what you can see in this case, one thing I want you to pick from here is, can somebody tell me something about the degrees of freedom? Compared to when we say var.equals to true. Do you notice a big difference in the degrees of freedom? Do we see a difference? The degrees of freedom has reduced, but we also have a decimal point in the degrees of freedom. Okay, so it no longer just counts the number of the numbers -1. It already does something else. It goes ahead and try to estimate the degrees of freedom. You can estimate the degrees of freedom. The degrees of freedom is, now when the degrees of freedom reduce, that means we are saying that we are getting less information from the data set when we assume that the variance are not equal compared to when we assume that the variance are equal. And in both cases, we still have some significant results. I can't explain apart from that I am different from you. I'm using a very older version of R, and for some reasons I've refused to update. Why I've refused to update R Studio is now that I'm using my Mac is very old. The system now does not allow me to update certain things, but I can get my way around. That is the only things that can happen. But you will also be able to do that with the time. Okay, so now let me see. Maybe, are you willing to give me 10 minutes? Okay, let's have just some 10 minutes. I run something so that tomorrow Susan starts. I just want to run and stop at just some correlation. Then tomorrow, we are not going to run the analysis of variance tomorrow. We first run the regression analysis, and if there is time, then we'll do it. But there's still going to be another training that Forum is going to organize. Okay. It's not next week. We still is. So let's go and run line 193. But before we do that, I want us to run line 190. The detach, run it as many times until you see something red. Run line 90 and you see red until you see red. For me, I've seen red already. Okay, so let's run line 193. Oh, you don't have empty cars. Okay, let me check whether. Oh, we don't have cars. That's fine. So, what can we do? Okay, let me first try to see if I can get cars. Yeah. Cars. Mm, mm, mm. Okay, I think let's not. No. I think I did not put in the file that I want. But I'm trying to see where I can get. Okay, I think we have that there. Okay, so what we are going to do, we are going to start modifying line 9, ignore line 193, go and modify line 194. Let me do something else like this. Data. Okay, so what we are going to do is we are going to make a modification. Type what you see in line 195. I want you to type car data, then you have empty cars. Once we do that, then we should be able to run the rest without any problem. How many people have modified line 195? Yes, I said empty cars, not car, empty cars. I know you're tired now, you're seeing double. Okay, let me show you. Oh, unable to start the video. Okay. Okay, so if you run that, I just want, if you're not getting it, that's okay. Let me just try to run it myself. So once you've done that, run that 195, then you can run the rest of the line. One 198. Okay. Now I want to show you something. Let me just run this line here, line 217 only. Then I let you go. I think you're tired. Oh. Let me just run this, then we call it a day. Everything seems to refuse to go. Okay, I just want to show you this. Then I can go. So what you need to do is you run from line 209, run line 210, and then from line 210, you can run line 217. I want to show you just some beautiful graphs here, and then we can call it a day. I'm trying to. Okay, I think so. I just want to show you something just, so forget about the Okay, so what we do, let's stop here for today. And then we can pick tomorrow after Susan introduces the topic of regression analysis. So I'd like to thank you for all the patience and that you've had today with me. I know I've been a bit rough, but sometimes it happens in life. But thank you very much for accepting to be tortured. Yes, I think we can hand over to the forum team.
My tool is there.
Thank you very much, Dr. Thomas Odom and colleagues for today. Let's wish the participants a good afternoon, nice evening, those who are morning, good morning. So until tomorrow. Thank you.